Today we will work with point estimation. This will be a very short introduction to the basic concepts. One of the goals of doing statistics is to draw insights or inference about certain aspects of the population using sample data. Some examples of this might be cases where we are interested in estimating, say, the average GPA of all students on campus, or perhaps the average time spent on recreational activities by students at UMD. There is an interest possibly in the age or the median age of everybody affiliated with the University of Maryland, or we might be interested in the median yearly income of all the people living in the United States of America. In each of these situations, we need to identify two characteristics. The first being the population that we are interested in, and secondly, the characteristic of the population that we are interested in. Before we proceed to describe these ideas, let us set up our problem. So suppose we have random variables x1 through xn. This is a random sample coming from a fixed population. Then in this setting, a point estimator for the population is going to be any statistic theta hat for the random sample x1, x2, x3, all the way up to xn. That is to say that theta check is a function defined on chi to the n to r, where chi is, or script x is the set of values for all the random variables x size. We would typically expect the values of our estimator theta check to be some sensible value of a certain population characteristic. This population characteristic would be typically called the population parameter and is usually denoted by the symbol theta. Note that the population parameter theta is fixed once we fix the population. Secondly, if we have population data, that is, we have all the information about the population available with us, uh, we can calculate the exact value of our parameter of interest, that is theta. But this is usually not the case. The population will usually be intractable, or you might not have access to every individual inside the population. And in this setting, we will have to resort to working with sample data to get an estimate for data. So suppose theta is a parameter of interest, um, and we are given an estimator theta hat for theta. Then recall that theta hat is a statistic which depends on the random sample x1, x2 up through xn. And the estimate theta hat, now when evaluated on sample data, will change every time our sample data changes. We are, of course, led to a very natural question. What do we expect the average value of our estimator theta hat to be in relation to the true value theta that it is trying to estimate? To answer this question, we will introduce the notion of the bias associated to the estimator theta hat. If theta hat is a point estimator for the population parameter theta, the bias of the estimator theta hat is denoted by bias of theta hat, and it is exactly the expected value of theta hat minus theta. Note that this is exactly the expected error when we use our estimator data hat to estimate a parameter theta using a random sample of size n. We say that data hat is an unbiased estimator for theta if the bias of data hat equals 0 for all possible choices of data. That is to say that the expected value of the statistic theta hat minus theta equals 0 for every possible value of theta. Notice that for a given population parameter theta, we can have multiple estimators, and in fact, we will soon see that we can have multiple unbiased estimators. But before we proceed any further, we will introduce the idea of ranking or choosing estimators from a group of estimators for theta. So suppose theta 1, theta 2 up to theta k are estimators for theta, then among all the theta i's, is there a notion of one estimator being better than the others? This is a natural question to ask. And the answer is provided by what is known as the principle of unbiased estimation, which says that among several estimators for theta, we would want to choose one that is unbiased. Let's work with some examples here. So suppose we are working with the simplest possible population that contains exactly two elements, 0 and 1, and it is endowed with the Bernoulli distribution, that is, the probability of getting a success x equals 1 is p. In this setting, suppose x1, x through up through xn is a random sample coming from this population, then we recall that the sample total is exactly the sum of the n random variables x1 through xn. And we also know that the sample total has the binomial distribution with parameters n and p. We can think of this as the sampling distribution of the sample total being the binomial distribution with parameters n and p. We now define p hat as t0 divided by n. This is the proportion of successes inside a sample of size n. P hat ends up being a very natural estimator for p, which is the true probability of getting a success in a single Bernoulli trial. We would want to analyze our estimator p hat for some of the properties that we have studied so far. For example, let us check if p hat is unbiased, and to do so, we would have to calculate the expected value. And as you can follow through this calculation, we notice that the expected value of p hat is in fact going to be equal to p for any given choice of p that we begin with. This says that p hat is an unbiased estimator for p. Let's work out another example. Suppose we were working with a random sample x1, x2 up through xn that is coming from a population with mean mu and variance sigma squared. We can define our estimator theta 1 hat to equal x bar, which is summation xi divided by n. This is exactly the sample mean. And we can define another estimator, theta 2 hat, which is x bar plus x1 minus xn. This is the sample mean plus the first observation minus the last observation. Notice that the expected value of theta 1 hat equals mu, and the expected value of theta 2 hat also equals mu. We can conclude that theta 1 hat and theta 2 hat are both unbiased estimators for the population mean mu. This is a case where we do not have a unique unbiased estimator for our uh, population parameter of interest, and as a result, we arrive at a situation where the principle of unbiased estimation does not guarantee a unique choice of estimator. Therefore, we must need additional criteria to rank our estimators theta 1 hat and theta 2 hat. To answer this question, we will have to study the variance of an estimator. So suppose theta hat is an unbiased estimator for the population parameter theta, then note that theta hat is going to be a statistic corresponding to a random sample x1, x2, x3 up through xn coming from the population, such that the expected value of theta hat would equal to theta for every possible value of theta. Then sigma squared theta hat is going to be defined as the variance of the sampling distribution of our statistic theta hat. We can now use the variance of an estimator to state the principle of minimum variance unbiased estimation, which says that among all unbiased estimators of the population parameter theta, you want to choose the one that has the minimum variance. The resulting estimator will be called the minimum variance unbiased estimator for the population parameter theta. To make sense of this principle, let us revisit example 2. So we know that theta 1 defined as the sample mean and theta 2 hat defined as the sample mean plus the first observation minus the last observation are both unbiased estimators for the population mean. To rank both of these estimators, we would calculate the variances of theta 1 hat and theta 2 hat. This calculation goes as follows. The variance of theta 1 hat is going to be the variance of x1 plus x2 up through xn divided by n. And notice that this is going to be 1 over n squared times sigma squared plus sigma squared all the way up to sigma squared n times. When you divide this sum divided by n squared, we get that the variance of theta 1 hat is sigma squared over n. Similarly, one can show that the variance of theta 2 hat is going to equal 2n plus 1 divided by n times sigma squared. Note that sigma squared is the variance of the population from where we are sampling. Notice that 2n plus 1 divided by n is greater than 1 over n for all choices of n, and that results in the variance of theta 2 hat to be bigger than the variance of theta 1 hat. Therefore, if we were to choose only between the parameter estimators theta 1 hat and theta 2 hat, we would have to choose the one with the smaller variance, which is theta 1 hat, that is the sample mean. Note that this does not prove that the sample mean is the minimum variance unbiased estimator. However, we have the following theorem, which says that if we were to sample from the normal distribution with the parameters mu, mean, and variance sigma squared, then the estimator sample mean is always going to be the minimum variance unbiased estimator for the population mean mu. We wrap this video up with a short discussion on the standard error of a point estimator. This is defined as sigma theta hat, which is exactly the square root of the variance of the estimator theta hat. This provides us with a measure of precision of the point estimator, and this measure is in the same units as the estimating quantity, right? This is also sometimes called the standard deviation of the sampling distribution of the point estimator theta hat. Note that if theta hat were to have a continuous distribution, then we might be interested in the probability that theta hat takes the value theta. Notice that this is exactly the probability that the estimator theta hat will take the value theta, which is the true value that we're trying to estimate. And because we are working with a continuous distribution, this probability is going to be zero. This means that even so, the point estimator provides us with an exact estimate for the value of theta, we have almost zero confidence that the calculated point estimate will actually equal the value that we're trying to estimate, that is theta. This leads us very naturally to other forms of estimation, specifically interval estimation, and that is something that we will address in a later video. But to summarize for today, we have introduced the notion of point estimators, we have introduced the idea of an unbiased estimator, and the variance of an estimator. And we stated two principles, the principle of unbiased estimators and the principle of minimum variance unbiased estimation. We did a couple of examples and we finally finished up with error estimates for our estimators. We will talk a lot more about estimators over the next couple of videos, but this is all for now. Take care of yourselves, and I will see you around.